Now we proceed to the method of sections. The method of sections is a process used to solve for the unknown forces acting on a member of a truss. The method involves breaking the truss down into individual sections and analyzing each section as a separate rigid body. This is usually the fastest and easiest way to determine the unknown forces acting in a specific member of the truss. In this method, we will cut the truss into two sections by passing a cutting plane through the members whose internal forces we wish to determine. This method permits us to solve directly any member by analyzing the left or right section of the cutting plane. To remain each section in equilibrium, the cut members will be replaced by forces equivalent to the internal load transmitted to the members. Each section may constitute a non-concurrent forces system from which three equilibrium equations can be written. Because we can only solve up to three unknowns, it is important not to cut more than three members of the truss, depending on the type of truss and which members to solve. One may have to repeat the method of sections more than once to determine all the desired forces. Now, we move to the steps in using the method of sections. The first step, label the members in your truss. It will help you keep everything organized and consistent. In this example, letters will be used for labels.
Second step, we'll treat the entire truss as a rigid body. Draw a free body diagram, write out the equilibrium equations, and solve for the external reacting forces acting on the truss structure. Third step, imagine cutting your truss into two separate sections. This cut should travel through the member that you are trying to solve for the forces in and should cut through as few members as possible. The cut shouldn't be in a straight line. Fourth step, next you will draw a free body diagram for either one or both sections that you created. Be sure to include all the forces acting on each section. Any external reaction or load forces that may be acting at the section. An internal force in each member that was cut when splitting the truss into sections. Remember that for a two-force member, the force will be acting along the line between the two connections point on the member. Determine whether it is tensile or a compressive force. A common strategy then is to assume all forces are tensile. Then, later in the solution, any positive forces will be tensile forces and any negative forces will be compressive forces. Label each force in the diagram. Include any known magnitudes and directions. Step 5. Write out the equilibrium for each section. You drew a free body diagram of these will be extended bodies. So you will need to write out the force and the moment equations. For 2D problems, you will have three possible equations for each section. Two force equations and one moment equation. For 3D problems, you will have six possible equations for each section. Three force equations and three moment equations.
The sixth and final step. Finally, solve the equilibrium for the unknowns. Using algebraically, solve one variable at a time, or use matrix equations to solve for everything. If you assume that all forces were tensile earlier, remember that negative answers indicate compressive force in the members. Example problem. The truss in figure T04 is pinned to the wall at point F and supported by a roller at point C. Calculate the force, tension or compression in members BC, DE, and DE from section to the left of A to A. The summation of forces at B equals 0. 5 over square root of 29 multiplied forces at BE equals 80 plus 60. Forces at BE equals 150.78 kilonewton in tension. Summation of methods at E equals 0. 5 multiplied to forces at BC equals 6 times 80 plus 2 times 60. Forces at BC equals 120 kilonewton with compression. Summation of methods at B equals 0. 5 multiplied to summation of forces at BE equals 4 times 80. Forces at BE equals 64 kilonewton in tension. We are group 6. Group members AGUDA, Jillien, Isidro, Antonio, Lucky, O, CASTOR, Kaithea, Franchette, and CRUZ, Angelo D, ELBANAN, Maha D, MAGCALAS, Rhoie T. Thank you.